Welcome to this problem-solving session. Today, we'll be tackling LeetCode problem number 82, remove duplicates from sorted list 2. In this problem, we'll be working with linked lists and focusing on removing nodes with duplicate values while retaining only distinct elements. This is a great problem to strengthen your understanding of linked list traversal and in-place modifications. Let's dive in and explore the solution together. In this problem, you're given the head of a sorted linked list. The key point is that while the list is sorted, it may contain duplicate values, and these duplicates always appear in consecutive positions. Your task is to remove all nodes that have duplicate values, so the final list only contains values that are distinct in the original list. The result should also remain sorted. Looking at the input format, you'll receive a singly linked list where each node contains an integer value, and the list is guaranteed to be sorted in ascending order. For the output, you'll return another singly linked list, but this one will only contain the distinct values from the input, also sorted in ascending order. Let's explore this further with some examples to understand how this works. In the first example, the input linked list is 1, 2, 3, 3, 4, 4, 5. Here, you can see that the values 3 and 4 appear consecutively more than once, making them duplicates. When we remove these duplicates, the distinct elements remaining are 1, 2, and 5. So, the output linked list becomes 1, 2, 5. In the second example, the input is 1, 1, 1, 2, 3. This time, all occurrences of 1 are duplicates since they appear consecutively. After removing these duplicates, the distinct values left are 2 and 3, and the output is 2, 3. These examples demonstrate how we handle consecutive duplicate values in a sorted list. In the third example, the input linked list is 1, 2, 3. Here, since there are no duplicate values in the list, the output remains exactly the same as the input 1, 2, 3. This shows that if the input list already contains distinct elements, no changes are needed, and the result will be identical to the input. Now, focusing on constraints, the linked list can have between 0 and 300 nodes, and each node's value falls within the range of -100 to 100. Additionally, you can always rely on the fact that the input list is sorted in ascending order. These constraints help shape how we approach the problem and ensure that edge cases are handled correctly. Let's look at some specific edge cases. First, if the input is an empty list, for example, there are no nodes to process, so the output is also an empty list. Second, consider a case where all elements in the list are duplicates, such as 1, 1, 1, 1. Since there are no distinct values, the output will be an empty list. Third, if the input is a single node list, like 5, there are no duplicates to remove, so the output is identical to the input, 5. Lastly, in a case of alternating duplicates, such as 1, 1, 2, 3, 3, 4, 5, 5, only the distinct values 2 and 4 remain after removing all duplicates, resulting in the output 2, 4. These edge cases highlight the different scenarios you may encounter and ensure the solution handles them appropriately. To start, let's consider the brute force approach. Since the list is sorted, duplicate values will always appear consecutively. The idea here is to iterate through the list, compare adjacent nodes to identify duplicates, and then skip over them to create a new list that contains only the non-duplicate elements. The process involves traversing the list and checking if the current node's value matches the next. When duplicates are found, we skip all nodes with that value and retain only the unique ones. While this approach is straightforward, it has significant trade-offs. The repeated traversal required to detect duplicates leads to a time complexity of O(n)(, and the need to create a completely new list adds an additional space complexity of O(n). As a result, while simple to implement, this method is inefficient for larger lists and not ideal for optimal performance. Now, let's focus on a more efficient solution, the optimized approach using a dummy node. Here, the goal is to handle duplicates in a single traversal while directly modifying the original list. To simplify edge cases, such as when the head node itself is a duplicate, we use a dummy node that points to the head of the list. 2 pointers, previous and current, guide the traversal. The previous pointer marks the last confirmed non-duplicate node, while the current pointer moves through the list. If a duplicate is detected by comparing the current node's value with the next, we skip all nodes with that value. If no duplicate is found, we advance the previous pointer to the current node. This approach is not only efficient, with a time complexity of O(n) due to the single pass, but also memory efficient, requiring O(1) additional space. While slightly more complex than brute force, it handles edge cases cleanly and avoids creating a new list. Additionally, there's the recursive approach, which takes advantage of recursion to process the list and skip duplicates. The base case occurs when the list is empty or contains only a single node, at which point the list is returned as is. For other cases, we check if the current node is a duplicate by comparing its value to the next node. If duplicates are found, we skip all nodes with that value and recursively call the function for the remaining portion of the list. If no duplicates are present, we link the current node to the result of the recursive call. This approach is elegant and concise, requiring minimal code, and it maintains a time complexity of O(n), since each node is visited only once. However, it comes with the trade-off of using O(n) space due to the recursive call stack, which could lead to stack overflow for extremely large lists. While visually appealing, the potential for stack overflow makes this approach less robust for very large inputs. The chosen strategy for this problem is the optimized approach using a dummy node. This method leverages key observations about the problem. Since the list is sorted, duplicates are always consecutive, and a single traversal is sufficient if duplicates are carefully skipped. The dummy node simplifies handling edge cases, particularly when the head node itself is a duplicate. This approach strikes the perfect balance between efficiency and simplicity, offering O(n) time complexity and O(1) space complexity. Unlike the brute force method, it avoids additional memory usage, and unlike the recursive solution, it eliminates the risk of stack overflow for large inputs. Although slightly more complex than brute force, it is far more efficient and robust, making it the best choice for solving the problem both effectively and reliably. To solve this problem, the goal is to remove all nodes with duplicate values from a sorted linked list, leaving only distinct numbers in the final result. We start by initializing two pointers, previous to track the last non-duplicate node, and current to iterate through the list. To handle edge cases, such as when the head node itself is a duplicate, we introduce a dummy node. This dummy node is placed before the head of the list and serves as a consistent starting point. The current pointer begins at the head, and as we iterate, we compare the value of the current node with its next node, current.next. This comparison helps us determine whether duplicates exist and guides the subsequent steps in the process. When duplicates are identified, meaning the value of current matches current.next, we skip all nodes with that value by advancing current until we reach a node with a different value or the end of the list. Once the duplicates are skipped, we update the previous.next pointer to point to current.next, effectively bypassing and removing the duplicate nodes from the list. On the other hand, if the value of current does not match current.next, it indicates that the current node is distinct. In this case, we move the previous pointer to the current node, ensuring it remains part of the result list. After handling either duplicates or distinct nodes, we advance the current pointer to current.next and continue this process until the entire list has been traversed. Finally, since the dummy node was used as the starting point, its next pointer will now point to the head of the modified list containing only distinct values. For example, given the input list 1-2-3-3-4-4-5, we start by initializing the dummy node, which initially points to the head of the list. The current pointer begins at the value 1. Since 1 is distinct, we move the previous pointer to 1 and current to 2. Similarly, 2 is distinct, so we move previous to 2 and current to 3. However, when we reach 3, we notice a duplicate, as 3 equals 3. We skip all nodes with the value 3 and move current to 4, updating previous.next to point to 4, thereby removing the duplicates. The same process occurs for the value 4, which also has duplicates. We skip all nodes with the value 4 and move current to 5, updating previous.next to point to 5. Finally, 5 is distinct, so we move previous to 5 and current to null, marking the end of the traversal. The resulting list is 1-2-5, containing only the distinct values. This approach has several key insights. First, the use of a dummy node simplifies edge cases, particularly when the head of the list itself is a duplicate. This ensures the algorithm remains clean and avoids additional complexity in handling special cases. The use of two pointers, previous and current, is also crucial. The previous pointer allows us to remove duplicates by updating links in the list, while current lets us iterate through the nodes and identify duplicates. Additionally, the algorithm is optimized by skipping all duplicate nodes in one pass, rather than processing each duplicate node individually. This reduces unnecessary operations and improves efficiency. Important edge cases to consider include an empty list, where the result is null, a list with no duplicates, which is returned as is, and a list entirely composed of duplicates, where the result is null, as the dummy nodes next will remain null. The problem primarily revolves around the linked list data structure, where each node has a value and a next pointer. The algorithm employs pointers effectively, with the dummy node simplifying adjustments, the previous pointer tracking the last non-duplicate node, and the current pointer identifying and skipping duplicates. In terms of complexity, the time complexity is O(n), since each node is visited exactly once, and duplicate nodes are skipped in a single pass. The space complexity is O(1), as the algorithm only uses constant extra space for the pointers. The sorted nature of the input list is leveraged to identify duplicates in O(1) time per comparison, making the algorithm efficient. By skipping duplicate nodes in one go, unnecessary traversals and pointer adjustments are minimized, ensuring an optimized solution. This solution removes duplicates from a sorted linked list, leaving only distinct values. We start by defining a dummy node that simplifies edge case handling, such as when the head itself is part of a duplicate group. The dummy node points to the head of the list, and we use a previous pointer to keep track of the last node that is confirmed to be distinct. The main loop iterates through the linked list using the head pointer. For each node, we check if it starts a sequence of duplicates by comparing its value with the next node. If duplicates are found, we skip over all nodes with the same value using a nested loop. Once past the duplicates, we link the previous node to the node after the duplicates. If the current node is not a duplicate, we simply move the previous pointer forward. In either case, the head pointer advances to the next node. Finally, the modified list is returned starting from dummy.next, which skips the dummy node itself. This approach ensures that all duplicates are removed efficiently while maintaining the structure of the list. Here, we define the structure for our singly linked list using the listNode class, which includes an integer value and a reference to the next node in the list. This class also has three constructors to handle different initialization scenarios. Now, in the delete duplicates method, we first create a dummy node with a value of 0 that points to the head of our list. This dummy node helps to simplify handling edge cases, such as when the head itself is part of a duplicate sequence. We also initialize a pointer, previous, to track the last distinct node as we iterate through the list. Then, we start a while loop to traverse the list using the pointer head. Inside this loop, we check if the current node is the start of a duplicate sequence by comparing its value with the next node's value. If they match, it means we've encountered duplicates. To skip over all nodes with the same value, we use another nested while loop, moving the head pointer forward until we reach a node with a different value or the end of the list. After skipping the duplicates, we update the previous .next pointer to bypass the duplicate sequence and connect to the next distinct node. If the current node is not part of a duplicate sequence, we simply move the previous pointer forward to the current node, as it is distinct. Regardless of whether duplicates were found or not, we then move the head pointer forward to continue traversing the list. Once the loop completes, all duplicate nodes have been removed, and we return dummy.next, which points to the head of the modified list. This approach ensures that we handle all edge cases effectively, such as duplicates at the start or end of the list, while maintaining a clean and efficient traversal of the nodes. In this example, we start with the input list 1-2-3-3-4-4-5. To simplify handling edge cases, we introduce a dummy node 0, which points to the head of the list. The previous pointer starts at the dummy node, and the head pointer starts at the first node, 1. Now, as we begin traversing the list, head points to 1. Since the next node exists and head.val is not equal to head.next.val, 1 is not equal to 2, we know there are no duplicates here. So, we move the previous pointer to head, making it point to 1, and advance head to head.next, which is 2. Next, when head points to 2, we perform the same check, confirming no duplicates because 2 is not equal to 3. Again, we move previous to head, making it point to 2, and advance head to 3. At this point, both previous and head have moved forward, and we're ready to continue analyzing the list. Now, when head points to 3, we find that head.val equals head.next.val, 3 equals 3. This indicates duplicates. To remove them, we skip all occurrences of 3 by advancing head to head.next.next, which is 4. Then, we link prev next to head, effectively removing the duplicates from the list. At this point, previous still points to 2, and the updated list is now 1-2-4-4-5. Next, head now points to 4, where we see another duplicate since head.val equals head.next.val, 4 equals 4. Again, we skip all duplicates by advancing head to head.next.next, which brings us to 5. We link prev next to head, removing 4 from the list. The updated list is now 1-2-5. Finally, when head points to 5, there are no duplicates, as head.next is null. We move previous to head, making it point to 5, and advance head to null, marking the end of the list. The final result is 1-2-5. In this second example, the input list is 1-1-1-2-3. Again, we initialize a dummy node 0 pointing to the head of the list, with previous starting at the dummy node and head at the first node, 1. As we begin, head points to 1, and we immediately find that head.val equals head.next.val, 1 equals 1. This signals duplicates, so we skip all occurrences of 1 by advancing head to head.next.next.next, which brings us to 2. Then, we link prev next to head, effectively removing all 1s from the list. At this point, previous still points to the dummy node, and the updated list is 0-2-3. When head moves to 2, we check again and find no duplicates since 2 is not equal to 3. We move previous to head, making it point to 2, and advance head to 3. Now, both previous and head have progressed further, and we're ready to process the next portion of the list. When head points to 3, we confirm there are no duplicates, as head.next is null. This means 3 is unique. We move previous to head, making it point to 3, and advance head to null, marking the end of the list. The final result for this example is 2-3. Next, in the third example, the input list is 1-1. Again, we start with a dummy node 0 pointing to the head of the list, with previous at the dummy node and head at the first node, 1. At this point, we're ready to handle this smaller list. Here, head points to 1, and we find that head.val equals head.next.val, 1 equals 1. This means the entire list consists of duplicates. To remove them, we skip all occurrences of 1 by advancing head to head.next.next, which brings us to null. Then, we link prev next to head, effectively removing all elements from the list. At this point, previous still points to the dummy node, and the updated list is 0-null. Since the list is now empty, the final result is null, which represents an empty list. The time complexity of this algorithm is O(n), where n is the number of nodes in the linked list. Let's break this down. The algorithm uses a single while loop to traverse the linked list. In each iteration, the head pointer moves forward by one node. This means that, at most, each node is visited exactly once throughout the traversal. Even when duplicates are encountered, the inner while loop simply skips over the duplicate nodes without revisiting them. This ensures that the overall traversal still only takes O(n) time. In the best case, where there are no duplicates, the algorithm performs a straightforward traversal of the list once, again resulting in O(n) time. In the worst case, where all nodes have the same value, the inner loop skips over all the nodes, but each node is still seen exactly once. This consistent behavior across all cases gives the algorithm a linear time complexity of O(n). Now, let's discuss space complexity. The algorithm has a space complexity of O(1), meaning it uses a constant amount of extra memory, regardless of the size of the input. To understand this, consider the memory usage. The algorithm uses a few fixed variables: dummy, which is an additional node for handling edge cases, previous, which tracks the last non-duplicate node, and head, which is used to traverse the linked list. Since no additional data structures, such as arrays or hash maps, are used, and the operations are performed in place, the memory usage does not grow with the size of the list. There are also no recursive calls, which would otherwise add to the memory footprint. Because of this, the space complexity remains constant at O(1). Let's compare this optimized approach to a more naive solution. A brute force method might involve using a dictionary or hash map to store the frequency of each node's value. Then, a second traversal of the list would be needed to construct the result. While this approach also has a time complexity of O(n), it requires O(n) additional space to store the frequency data. In contrast, the current solution avoids such extra data structures by directly skipping over duplicate nodes during a single traversal, reducing the space complexity to O(1). For the time complexity, we can mathematically prove that each node is visited only once, even in the worst case, leading to O(n) time. For space complexity, the absence of extra memory usage or recursion keeps it at O(1). In summary, this optimized approach achieves O(n) time complexity consistently, while being significantly more space efficient with its O(1) memory usage. When solving this problem, one common mistake is failing to leverage the fact that the input list is sorted. The sorted property can be incredibly useful for simplifying the solution, as it allows us to detect duplicates by comparing consecutive elements. Ignoring this property often leads to inefficient solutions, such as iterating through the entire list unnecessarily or using additional data structures like hash maps, which increases time or space complexity. Another frequent issue arises when removing elements in place. If you don't properly adjust indices after a removal, it can result in skipped elements or even infinite loops, causing logical errors. Lastly, overlooking edge cases like an empty list or a single element list can lead to runtime errors or incorrect outputs. Always account for these scenarios to ensure your solution is robust. Another common pitfall is misinterpreting the problem requirements. For instance, there's often confusion about whether duplicates should be removed entirely or if one occurrence should be retained. Misunderstanding this distinction can lead to solutions that don't meet the problem's expectations. Additionally, some solutions overuse auxiliary space, such as creating new lists or using data structures unnecessarily. Since this problem can typically be solved in place, excessive use of extra space not only violates constraints like O(1) space but also reduces efficiency. Ensuring a clear understanding of the requirements and constraints is key to avoiding these issues. In interviews, there are a few patterns and strategies to keep in mind when approaching problems like this. First, always check if the input has useful properties, such as being sorted. Problems like these are often designed to test whether you can recognize and exploit these properties effectively. Techniques such as sliding windows or two-pointers are particularly useful for working with sorted arrays or lists. When optimizing your solution, interviewers look for your ability to move beyond brute force approaches, especially when constraints like O(n) time or O(1) space are emphasized. Another important aspect is explicitly discussing edge cases. For example, mention how your solution handles empty lists, single elements, or lists with all duplicates. This demonstrates a thorough and thoughtful approach. Finally, restating the problem to confirm details like whether duplicates should be removed entirely or partially retained can help ensure that your solution aligns with the requirements. This problem is closely related to several others on LeetCode, which can help deepen your understanding of the concepts involved. For instance, LeetCode 26, Remove Duplicates from Sorted Array, is a simpler version where the goal is to retain one occurrence of each duplicate. Similarly, LeetCode 83, Remove Duplicates from Sorted List, tackles a linked list variation with the same objective of keeping one occurrence. The problem we're discussing, LeetCode 82, focuses on removing all duplicates entirely, leaving no occurrences. Lastly, LeetCode 80, Remove Duplicates from Sorted Array 2, introduces a twist where each element can appear at most twice. Exploring these related problems can give you insight into different variations and the techniques required to solve them. There are multiple approaches to solving this problem, each with its own trade-offs. The two-pointer approach is a popular choice. It uses a slow and fast pointer to iterate through the list, skipping duplicates and overwriting elements in place. This approach is optimized for O(n) time and O(1) space but requires careful management of indices to avoid errors. Another method involves using a hash map to count occurrences and then constructing the result list based on those counts. While this approach is simpler to implement, it uses O(n) space, which may violate constraints. Lastly, for linked lists, a recursive approach can be elegant. It involves traversing the list recursively and removing duplicates as you go. However, this method has an O(n) space complexity due to the recursion stack, which can be a drawback in environments with limited stack size. Each approach has its strengths and weaknesses, so choose based on the specific requirements and constraints of the problem. Great job! To summarize, we explored how to efficiently remove duplicates from a sorted linked list using a two-pointer approach. The key takeaways include mastering linked list traversal and using dummy nodes for edge cases. Thank you for watching, and I encourage you to practice similar problems to solidify your understanding. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!